Hello and welcome back to another episode of the Oxford MAT Livestream. I'm James. I'm joined by Beth moderating chat again. Beth's a current student, keeping an eye on chat with me as well. If you want to join in chat, you can do that at slido.com/matle or follow the link on the Mat Live website, which is here and in the YouTube description, or the chat button on the Mat Live page that you came from to get here. And good to see so many of you here already, hanging out in chat. Hi to Aya and East the Eye Pie in chat. You can set kind of your name or not your name in Slido chat. One of the things I like is that you can be anonymous. Yes, like that. There's a few questions that have been coming in. I'm going to say that probably the best use of this live stream time is if we try and do some math questions together. I'm going to really quickly do ones that you can see on the screen at the moment. Somebody's asking about compass and ruler in the mat, and this year in Pearson test centres, the rule is that you can't take anything and you can't take any materials into the exam room. So I'm afraid that means no rulers and compasses, but also the questions are written so that you're not expected to have a ruler and compasses. Yeah, okay, so I don't know how you know if it's gone through the tab. I think you should assume that it's gone through correctly, and if you don't hear anything, follow up. But I think give them some time. Yeah, that's sort of right. Hi to Anna as well. There's hard questions about choosing test providers, which takes up a lot of the rest of my year. I'm smiling because obviously no comment. Right, cool. Okay, everyone happy? Well, let's find out. We have a poll for that, don't we? You can tell us how was your day today on a five-star scale, not a 5-scale star, which would be a very small fish. And let us know in chat what's going on. Hi to it. Yeah, there's an anonymous person who just says hello, James, which is nice. Good. I'm having an okay day. I'm always watching out for people who are having a 1-star day, who are there in chat, and they're having a terrible day. I got caught in the rain yesterday, so maybe that was a 2-star experience. Obviously, I don't know what's going on in your life, but hey, here are some maths questions. Let's find out if that makes things better. Good. Okay, my plan is that I've picked out 4 or 5 questions that I think look interesting. They're just ones that I think look interesting. If you've got ones that you've tried from 2013, 14, 15, then you could let me know in between. If it looks like I'm wondering what to do next, you can let me know. I think I'll pick first. I've got first question I'd like to do, that one from the thumbnail, but then some audience interaction to choose what we're up to. Sophie says their school just nearly caught fire, which sounds like pretty bad news, pretty bad day, but I suppose we should reserve a star for kind of obvious, slightly worse thing that could happen. And an anonymous person wants to know whether the British Maths Olympiad is good practice for the mat. I suppose I'll say yes, sort of, in a way, in that doing any sort of maths competition or maths challenge or maths test or anything mathematical is probably good experience for the Oxford maths test, because you're practicing solving maths problems and more generally solving problems. My general advice is anything that you can't do straight away is probably good practice for solving problems. It doesn't really matter where you get the problems from. There are some key differences between Olympiads and the MAT, which you might notice by looking at the syllabus of what maths is covered in those things, and a little bit in the style of questions, and of course in the format of the test, stuff like that. Good, okay, I think we're going to leave that there at a sort of tie between 4 stars and 5 stars, which is, it just broke. Did you see that? Just as it turned up, somebody voted 4 stars. So it's a victory for a 4-star day, which is pretty good, I guess. Unless this is like an Uber rating system, in which case 4 stars is terrible. Good, and hello to Ayn in chat, there we go. Yes, interviewers ask questions. If you get invited to interview, the questions are not limited to a particular syllabus, and could even teach you some new maths that's not in A-level at all. Interviews are quite different because the interviewers are there to maybe teach you something or explain something, to work with you on a problem, which means that we're not restricted to precisely things that you've definitely seen before. They're testing slightly different skills, I suppose. Matt has got at least partly questions about A-level fluency, and then by the time you get to being interviewed, if you're interviewed, we know at that point that you're not having trouble with A-level, and that frees us to ask about other stuff. Right. So yeah, the syllabus is the syllabus for the maths submissions test. If you would like a copy of that, you can find it at the maths submissions test website. It's a single page of paper with a list of topics on, and something we've been doing on this show, on this YouTube channel, is to work through all of those topics and revise them. So you could look at previous videos on this channel if you want to see content on that, or just go to my live stream page and get hold of the worksheets that we used if you want to see some revision questions on particular topics, because what we're doing at the moment is going through past papers, which kind of do a bit of everything all at once. So that's the menu of what we've got. We've got specific live streams on particular topics, which are in the past, and they're on that live stream page and this YouTube channel, and we've got this one, which is in the present, if I ever stop talking about it and start doing some maths questions. Right, okay, if that's all right with everyone, I think I'm going to switch off chat on screen, so I can still see chat, but I'm freeing up some screen space so that I can fill the screen with logarithms. There they are. So this is a question about logarithms, but secretly it's about equations. It's about solving some equations in here somewhere. It's one of those math questions where you're supposed to complete a sentence. The sentence says this information, and then there are some options about what might be true. And I think something that you're supposed to notice is that these are asking about how many values of A there are that are sort of consistent with this information. We've been given some information about A and B and C, they're positive numbers, and some logarithm facts. And it might be the case that this is enough information that we know which value of A they're talking about, specifies it uniquely. It might be the case that this is satisfied by two values of A. It might be infinitely many values of A that this works for, given finding B's and C's. And it might be the case that there are no such values of A that do this. So it's sort of 0, 1, 2, infinitely many. How many solutions are there, if you prefer to think of it like that. A different way to think about it is if it wasn't logarithms, I'll just cross them out for a second. If it was something like A squared equals 1, B equals C, or something, some really silly pair of equations like this, then the answer would be that it's satisfied by two values of A. That we can get two values of A, 1 or minus 1, specified by this. Of course, loads of possibilities for B and C, so long as they're equal to each other. But if these were the equations, we would say that there are two values of A that satisfy all this information. Oh no, it says positive. Rubbish! It says positive. Ah, I missed a piece of information. Very annoyed. Very annoyed with myself. Pretend that I didn't say A squared. Pretend that I said some sort of quadratic with two positive roots. Minus 2A or something. So now it's satisfied by. Is 0 positive? Rubbish. Add, make it 3 and 2. Oh, I'm having a terrible day here. Something that's satisfied by two different positive real values of A. Maths is really hard, right? You think you made a great point and then you realise that you made an incorrect point. They're so close together. Right, okay, anyway. Forget my equations, which are now gone. We're dealing with some logarithms here. So perhaps something we should start with when we see equations like this is to work with the kind of corresponding facts about powers. Each one of these equations has a corresponding fact, right? That this one means that A is B squared. And these facts are interchangeable if B is a positive number, if A is a positive number as well, because you can do logarithm base B on both sides. And that's well defined if B is positive, and it does the sensible thing when you can also do B to the power of both sides. Okay, and then over here we can do something like this and something like this. Okay, so this gives us three equations, and I think I'm much more comfortable working with these three equations with powers in than I am working with logarithms. So, any ideas? Let me know in chat. Any ideas when you have these three equations and you want to see what kind of follows? What can we say from this? I guess we want to work towards having some sort of, well, ideally solution for A and B and C, I suppose. But let's know, if A is just the number 3, then I would like to know that, because if it's just the number 3, then we've specified A uniquely. It might be the case that something weirder than 3, square root of 3 or something. Put it all in terms of B, says an anonymous person in chat. It's a good idea, I think. Try and eliminate variables to try and get rid of the A's and C's. Why have you gone for everything in terms of B? Maybe there's a reason in terms of, maybe B is easier to write stuff in terms of, because you've got this statement for C in terms of B and this statement for A in terms of B. It'd be nice to write everything in terms of A, of course, because the options are all about A. Yeah, that's quite, actually I'm quite tempted to do the other way around. I know what you mean though. Let's start by eliminating C. Matthew in chat says eliminate C. Well, I suppose the anonymous person wants me to eliminate C as well, so I'll do that, I suppose. So if I eliminate C by writing over here, C is B cubed plus 3, and I can put that in here to turn this statement into B cubed plus 8 equals A squared. So I'm substituting in this fact about C. I've got some information about C. I know that it's B cubed plus 3. If I plug that in here, I get this fact. And then I suppose the choice is, do I either get rid of the A by replacing it with a B squared, or to get rid of B by replacing it with a root A to the power of 3. Feels a bit unpleasant. And there's a suggestion in chat that so Ian wants to eliminate A. There's another vote for 2 equations in terms of B to get B equals, and then another vote for getting B equals something. How bad is this going to be? I suppose if we find values for B, then I can remember that the value of A is just the square of those values. So a unique solution for B would give me a unique solution for A. 2 values of B, I would have to think a little bit. 2 positive values of B, I wouldn't have to think very much. Okay, I'm willing to eliminate A, even though the options are all in terms of A. Let's do that. So if I take A equals B squared, and I'm going to plug it in over here, I get something like B cubed plus 8 is equal to B to the 4. Now I feel slightly unwell because I've got a polynomial in B that is enormous degree. It's got degree 4. So that's quite bad news for me, isn't it? Let's see if I can do anything with this. Could try guessing solutions that work. 8 is 2 cubed, and I've noticed that if I put 2 cubed in here as well, then I get 16, which is 2 to the 4. So I think that because this is true, 16, 2, 4, 8, 16, take away 8. Because this is true, I think that 2 is a solution to this equation. So B equals 2. Maybe question mark, because there might be some other solutions as well. I suppose this whole question is about how many solutions there are. Kind of feels like there might be 4 solutions, right? But 4 solutions is not one of the options, so I should keep working. Right. Okay, so let's put this in like square brackets because it's kind of something I'm thinking. And then we'll do polynomial division, I suppose. So I'll try and bring out the factor of b minus 2 to work out what the alternative is. And that's going to be something like minus 2b cubed plus 2b squared minus, so then I've got minus 4b squared. I don't want minus 4, oh no, I don't want to add 2. Back up. I'm going too fast. Okay, so I write down the b cubed so that I get b to 4. Minus 2b, I've got minus 2b cubed. As a result, I don't want minus 2b cubed, I want minus b cubed. So I'm going to cleverly add b squared so that I get a b cubed back again. That gives me minus 2b squared. I don't want minus 2b squared, I want none of them. So I'll add on 2b. That gives me 2b squared back again. Haha. But minus 4b, I don't want any b's either. So I'll add minus 4b, I'll add 4 so that I get plus 4b. And also that gives me minus 8. Good. Now what? now I've got a, what is this, some sort of cubic? Sort of cubic that, and then the question is going to be whether this has any positive solutions B. I think I'm stuck. Well, I'm skeptical. I think it probably doesn't. People in chat, two of them have posted exactly the same cubic, which is helpful for me because I can check my answer now. They agree with each other and with me. Good. Okay, thank you, chat. And now what? So I suppose I've got b equals 2, or what? Or does this cubic equal 0 for any positive numbers? Well, I suppose probably not. Yeah, so in chat, I think somebody's put this into a cubic formula or put this into their calculator. Matt's got no calculators, so I think I'm going to have to give you a reason why. My suspicion is that this has got no positive solutions. My suspicion is that all of these signs are plus signs, so it looks positive. It's not a real argument, right? But it looks positive if B is positive. Yeah, that's good enough, isn't it? If B is positive, then all of these terms are positive and not 0 because of the 4. So this is definitely not 0. So no other positive solutions. When we put 2 in, we have these minus signs and this -8. Very good. It meant that even though 2 is positive, we could subtract some stuff down to get to 0. Why am I still talking? We've got no more positive solutions, so just b equals 2. And then a is 4. And I guess we should work out c just to check. Not really sure what you would say of. I guess it could still be is contradictory, because we should still check that there is a value of c, but everything's fine, isn't it? C is just 11. That's consistent with this equation over here. 8 really is 2 cubed. And it's consistent with this equation. 16 really is 4 squared. So I think it specifies a uniquely, and the answer is 4. Yes. Yes, there's a suggestion in chat that I should differentiate this, and that is actually what I was thinking a moment ago, which is that when you differentiate this, you get a quadratic, and then we could check that this quadratic is positive by completing the square or something. But that felt like 2 steps at a moment when really I wanted 1 step. So complete the square, prove that that's positive, or at least positive for positive b. Certainly looks positive to me. So then it's an increasing function. I guess all of these terms are positive as well. Even without completing the square, we can now point at the derivative and say, well, all these terms are positive because that's got a square in. 2b is positive, and 2 is positive as well. Good, right, okay. I think that specifies a uniquely. Having fun. Somebody says c equals 11 in chat. Thank you. Yes, I agree. So I think people found this question quite hard. I've certainly talked to people who find it difficult over the years, and I think that's because it's asking you for information and it's asking you about properties of the solution rather than just asking you, what's the value of c. It's exactly the same amount of work to find at the bottom there c equals 11 to get to this point that this person in chat says, c equals 11 at the top. That's exactly the work that we've done to work out b is 2, a is 4, and I guess c is 11. The tricky thing is the question doesn't tell you to do that. The question gives you some information to see what you'll do with it. And maybe that's a fact about MAT that we can think about more generally, that if the question just gave you an instruction and said, find a, b, and c, you'd be off and away, no trouble, right? Here are some equations for solving them. Because the question is phrased in terms of properties of the solution, it's almost like getting you to think about whether you've found all the solutions and getting you to think about what the nature of your solution is, rather than just turning the handle. That puts people off a bit, I think, in terms of maybe it prevents people from just jumping in and solving the equations. Although just jumping in and solving the equations is how you make progress with the question. So we've got to find that balance, right, between cautiously thinking about what we need to do in a question and adventurously just trying stuff to work out what's true. What can we do with this information? Probably you're used to the second way of thinking a bit more, because everything in A level or equivalent, I think, is just jump in and get going. And then it is technically tricky. Sorry, yes, good point in chat. This is like sort of technically tricky. I got a bit stuck down here. You've got this b to the 4. I said that I felt sick at one moment because, you know, I wanted a nice quadratic. I got a power of 4, and I guess if you plugged this in the other way, which is something I considered, then you could have you'd guess a power of 3/2. You might then square something to get a worse polynomial for A. I'm going to quickly experiment to see what happens if I do that. If I'd gone the other route through the forest or something, right? So I was considering writing B is the square root of A. So my equation up here is something like A to the 3/2 plus A is A squared, which is a very similar equation because of course A is B squared. And then I guess I would rearrange it and things would get a little bit nasty. Oh, I guess so. This is after I subtract 8 from both sides. I get something like this. This is a 3 from squaring correctly. Maybe it's good I didn't try and go in this direction. And then I've got a degree 4 polynomial, which has got solution 4, because that's the solution. But my ability to spot that 4 works hinges on doing large powers of 4. 4, 16, 64, 256 minus, oh my goodness. So somehow finding the root of 2, b equals 2 over here is easier than finding the root of a equals 4 over here. Okay, no way to know that, I suppose. I guess don't introduce powers of 3/2 if you have the option to introduce a power of 4 straight away instead. You might have to do more squaring. Okay. Yes. Okay. Someone in chat is using complex numbers for this, which is interesting. Oh wait, maybe that's not a complex number. That's just let b equal to I or something. No, wait. I don't know what they've done. Someone in chat has got some complex numbers, possibly. Right, okay. Just in case anyone needs to hear it, complex numbers are not on the MAT syllabus, which means that the questions don't need you to know what complex numbers are. So if you don't know what complex numbers are, then you're in for a treat in the future when you find out about complex numbers, but you should be able to do the mathematician's test without knowing about complex numbers. The questions are also supposed to be designed so that knowing about complex numbers doesn't make the questions easier. But no, yeah, and with maybe 1 or 2 exceptions, I think we'll do that quite well. Right, okay, that was a question that I wanted to do because it's in the thumbnail. I'm aware that last week we did the question in the thumbnail right at the end of the video, so anybody who just clicked on it to find out the answer or to find out more about that question had to wait 2 hours. This week I've done it straight away, so if you're here again, welcome back. I guess it wasn't clickbait the second time, but you know. Good. Yeah, it was Beth in chat is for a big fan of complex numbers, which I will now broadcast on stream. There you go. And complex numbers are cool. You will enjoy them. Right, okay. But we should do a math question, which won't involve complex numbers. I'm sorry. Can I have suggestions, please? If you've tried these past papers, we're looking at 13, 14, and 15. If you've tried these past papers and there's a particular question that you really want to talk about, or even just one that you think would be interesting to work through and get other people's opinions on from chat, my opinion, I guess, then let me know in chat. Otherwise, I'm going to do one of, there's a long question over here that I think is fine. There's a request for 1J already. Oh, question 2013, question 3. Hang on a moment, because I think 2013, question 3. Did we do this one? No, we previously tried this one on MAT Livestream in previous years. So point taken. And there's a request for 1J, which is powers of 2 again. Okay, powers of 2. But this is come up a few times, right? So this largest number less than or equal to x says you're taking 2 to the x but rounding down. So that means something like working out. There's some steps in here. For a while, it's the value is 1, and then it goes up to 2, and then 4, and then 8 and 16. And the challenge is to work out when do these things happen. When does it switch to the next power? If you can do that, and if you can write down the size of all the rectangles, because the area is made of rectangles in this case. I don't mean in like a definition of integration sense, I just mean graphs full of steps and rectangles. So it should just be the sum of those. It's then, I know it's hard because it involves simplifying some terms involving logarithms. Maybe we'll come back to this one. There's a request for 1i, which is the other question on this page, which is a good request because we've done a few questions, a little theme from last week and the week before. So we've done these questions with functions involving you're given some values and then you're told about how to get new values according to the kind of binary expansion of the number, if you like. And that's a little reference back to previous questions we've talked about. Okay, so let's stick on question 20. Let's stick on 2013 for a little bit, and then I do see there's a vote there for 2015 1D question mark, which I'll try to remember. Sorry if I forget. I think we'll do a couple of these 2013 questions, because that's what people seem to be voting for right now. Okay, that long question, I'm probably not going to do all of it, but I'll try and pick out the good bits. You can tell me while we're doing it, Cougar H, whether or not I picked out the correct bits. Okay, chat's vanishing a little bit. I can still see it. Beth can still see it. I need space. need space for my functions. What have we got? We've agreed, I think, that a sensible thing to do is to work out the first few values. Like for this one, if you see an even number, just look back at half that number, which you can do because it's even. So I don't know about 5 yet, but F6 is just the same as F3. F7, F8 is just the same as F4. Powers of 2, all going to give me the value of 1. F of 9, I don't know yet because I haven't read this statement. Okay, time to engage with the concept of odd numbers. Those say, oh, just look at the previous value according to this rule, which is slightly weird, right? So here, if I put in the number 2, which I'm allowed to do, if I put in k equals 2, then I get f of 5 is f of 2. Over here, if I put in k equals 3, then I get 7 on the left and f of 3. Sorry, I get f of 7 on the left and I get f of 3 on the right. So that gives me this minus 1. Okay, that's interesting because that's giving me a minus 1 over here. It was the same as f of 3. So it's kind of interesting because there's going to be a lot of 1s, aren't there? Like this one, f9. That's what you get if you put k equals 4. I'm sorry for the background noise. That's some drilling going on somewhere in the building and it's coming through the walls. F4, actually the value 1. I think I need some more data. So far we've only got minus 1 here and here and here, 3 and 6 and 7. I haven't spotted a pattern yet. So I think I need some more. The worst case scenario, I work out 100 of these. It will take me ages, but I work out 100 of these and then I add them together. What have we got then? F10. Is there a quicker way to do this? Doubling? F10 is the same as S5. I think I want to work out which ones give me minus 1. So which ones give me minus 1? The question then is, I have something like 3, and if you double it or add 1, and then if you double it or double it and add 1, double it or double it and add 1, you get these things will all relate back to give me minus 1. There's a pattern here. So if I put 12 into this left equation, I get f of 24 is the same thing. And if I put 12 into the right equation, that gives me 25. 13 gives me goes to 26 and 27. I'm saying goes to as if I'm working from the right hand side. I put in that number, so f15 I'm about to do. That will give me f of 30, f of 31. There's a real pattern here to how many of these are the only things that are going to give me minus 1 because everything else is going to relate back to the other numbers. Right, in chat there is a much better idea to start doing the sum. And there's some powers of 2 stuff going on, isn't there? Because this is 1 less than the power of 2. so is this, so is this, so is that. I think I might do one more row and then see what I've got. So this will be 48. The next, these numbers are all in a sequence, aren't they? All the way up to 63. And then the next number that I would put down is 96 or something, which is still less than 100. So 96, 97, 98, 99. Somewhere in here there's 50, 51. So 100. These things all give me -1. So if I just count these, that's the number of times that I get -1, and all of the others will give me +1. So I have a counting challenge. The snazzy thing to do would be to count how many are in each row, to say something like +5 down here, because it's branching each time, so the number of things in the row is doubling. So I get 3. Adding these together gives me, oh come on, that's geometric series. Adding these together gives me 31 things, I think. Almost 32, but not quite. And then that's a 36th thing. So I think I get 36 votes for -1, and the others out of 100 give me +1. Oh, I really hope this is one of the options, because this feels like I've done a shortcut. So I'm going to get 28, I think. Take off, so 30, 28, which is one of the options. So that's pretty good. Everyone in chat is telling me that I'm doing this wrong, and that I should be looking at cancellation, right? So everyone is saying that if you add up the sum as you go, then you find a whole string of -1s that cancel out. The numbers I haven't written on here are 8, 9, 10, 11, and they cancel with 12, 13, 14, 15. Right, so the sum cancels out every time you get to something to do with the power of 2. Maybe it's every power of 2 or something. The sum just cancels out. Doesn't explain why it's 28 though in the end. Maybe I'm wrong. 4, 5, 6, 7. Oh. Not. Okay. Yeah, such as the thing that I've counted this wrong, but that's just me. Chat's going to let me know in a second. I'm picking B, but I feel a bit wrong. Yeah, so the popular thing in chat is to say that F1 is 1, F2 plus F3 is 0. They cancel. And then, oh, there's a whole stretch from 64 up to 95 that only gets to cancel. It should be cancelling with everything up to 127, but we're missing quite a lot. We're missing quite a few things. We're missing 27 things, and we have f of 1 at the front, so that's why it's 28. Because we're missing all of this stuff before we get to some good cancellation. Or said differently, because 28 is how far it is until we get to the next power of 2. Okay. Well done, people in chat, spotting powers of 2 are the points where it cancels, or doesn't cancel. Points where it does cancel. Quick maths. I might be up by 1. In my reasoning, not in my answer anymore, I think. This question's fun. I don't think I've done this question for years. I'm slightly underprepared for this MAT livestream, can you tell? And I've forgotten who picked this question as a thing for us to do. It was an anonymous person who picked this question as a thing for us to do. Good pick. We've done a few of these with functions like this. The fastest way is presumably to look at power of binary, what's going on in binary, which is something like it's the things that start with 1, 1, because this rules at the top here tells you about the first 2 digits of your binary number. If they're 1, 1, the first 2 digits of your binary number, something like that. Yeah. So then after that, you write more stuff on the end. So you have either 1, 0, 1 or something. Does this rule follow from that one? Doesn't follow from that one. That's a bit weird. If you start 1, 1, then whatever you write afterwards, following these rules, you still get the same value. If you start 1, 0, which is like this 2 in here, then everything afterwards you get the same value. Right, the value f1 doesn't really affect stuff, does it? It's nice that they put a 1 in here, but it doesn't really change what's going on. Interesting. Why is there a +5 in the bottom right? Yeah, it's my terrible notation. So I was trying to count stuff. I had 1 thing, so I wrote 1. Then I had 2 things in this row. There are 2 things. Then I had 4 things, so I wrote 4. Then I spotted a pattern. I wrote an 8 and then 16 for doubling. But then because our sum, the ones I'm interested in, I stopped at 100 because in the question, the sum wants me to stop at 100. And that means that in this row, I don't want to go all the way from 96 to 127, which would be a plus another 32 things. I just want 1, 2, 3, 4, 5 of them, if I'm counting how many of them there are up to 100. There's an awkwardness here that the question contains a really cool thing that goes on every power of 2 that maybe you could spot, that every power of 2 is cool, but then it asks you about 100, which is not a power of 2, so it's awkward. Yeah. 2 complementary questions have come in chat. One is, in the new 2024 MAT, will the problems be from all 1%? The problems are just, the problems for 2024 MAT were written for 2024 MAT, I think is the most that I can say. There are some multiple choice questions, and there's 2 long questions that everyone is doing. And there was a question about, should maths only students prepare by doing problem 6 and 7? And I guess maths and CS students prepare for problem 4. My kind of hot take on this is that maths and CS students, I think, probably should be able to do past paper questions on questions 4 and 6 and 7. You've never, people doing those past papers didn't have to do them. But I often look at question 6 and 7 and think, yeah, this sort of seems all right. Let's have a look at this one now. So here's a logic puzzle that is just fine. I think maths applicants should probably be able to do this question because it's just writing numbers and thinking about prime numbers. And maths candidates know what prime numbers are. So we'll look at question 4 from 2013. So this question is disguised as a geometry question, but really it's about ratios and trigonometry. And I guess those things don't come up quite so often in computer science as they do in maths. So in 2013, computer scientists did this question 7 instead. But this question is about working really systematically in what is secretly pretty much like a logic. It's a grammar, right? It's got rules about what you do and how you can get from one thing to another thing. And it feels slightly algorithmic when you're doing it, but it's just a puzzle that it's just a sort of problem that I think anyone who's up to date with the maths syllabus, you don't really need much of the maths syllabus for this question, but it's about working logically. So my sort of hot take is that, yeah, you can look at these past paper questions. They're out there, and remembering what I said before, basically any sort of maths questions that you can't do straight away, including computer science questions, even if you wouldn't have done them on the actual test if you'd applied 10 years ago, still interesting. Sort of want to do question 7 now. Yeah, kind of want to get sort of, what's the word for when you see a maths question and then you don't really want to move on from it? I haven't done this one in ages. So there are words that are made of the letters A and B, sort of mathematical words such as but without worrying about whether that's in the Scrabble dictionary or something. Basic rules are it can be replaced with a word that starts with A followed by X, ends with B, like this. It's a good notation for that. And you can remove a B from the end. So then, where do you start? Starting with the empty word. Okay, so I'm going to go empty word, and from the empty word I can go to using rule 1. Using rule 1 I can get to AB. I can't use rule 2 because I can remove that empty B. And then I can use rule 1 again to get to two A's and two B's, writing an A on the front and a B on the end. Then I can use rule one more time to get to three A's and three B's. And then I'm going to use rule 2 twice to remove two of those B's in the kind of obvious way to get down to AAAB. Okay, that's nice. There's maybe a graph or a chart I could draw of how you get from a certain number of A's and a certain number of B's. Oh, that's part 2. Part 2 is to think about all the things that you can make. It's going to be A's followed by B's because the A's are always getting added to the front, B's are always getting added to the end. And you can remove some B's. So I think it's, I think it's A to the I, B to the J with J less than or equal to I. And my solution for this part is going to have to put in words on the page why I can make all of these things and also why I can't make anything else. And that's not too hard because anything else would have A's and B's mixed up, which I obviously can't achieve with rule 1 or rule 2. And it would maybe, or it would maybe have more B's than A's, which I can't do because the first rule introduces them in even numbers and then the second rule removes them. This is fine. New rule, and it's fun. Reverse the word, flip it and reverse it. Replace every A by B and every B by A. Fantastic. So applying that to the thing we already had gives us, so reverse it gives B A A A. We briefly make a kind of sheep noise, but replace every A by B and every B by A gives us this. I guess this happens simultaneously to give us this. Okay, describe all the words that can be made now. Well, hang on. Before I can make any A to the I, B to the J, so I should think about those with a bit of reversing in the middle. Oh, but this reversing still gives me something that starts with A's and ends with B's. I think it's now the case that I can make A to the I, B to the J for any like I and J, even if you want more B's, because first I'll make lots of A's and then flip it. And I think it's pretty clear that I can't do anything else. You might think that reversing in the middle or doing the flip in the middle would help, but what are you going to do next? Well, flip it back again or add more A's and B's to the front and end, which just gives you more of these A to the I, B to the J words. And my claim now is you can make all of them, so I'm really bothered about doing it a fun way. Okay, good. And now at the end, make everything, and that's the fun bit. Oh, for arrows, you've noticed that I'm writing arrows, and on the test this year, you can't type an arrow system using a standard keyboard. You're answering with a keyboard. I guess if you wanted to write an arrow, you could write dash and what is that, dash greater than symbol? But I mean, if the test wants you to do that, they'll probably explain that they want you to do that. You say that nobody's stressed about it during the exam, so that you don't have to have seen that last 30 seconds of video or something to know what an arrow looks like. And yeah, I can't really imagine it, but yeah, it's sort of verging on ASCII art, isn't it? Where you start trying to draw diagrams with symbols. So maybe I should say very clearly that drawing diagrams with symbols is not an intended thing that's going on with MAT 2024. It's not the case that this is now like a sort of keyboard skills thing where people can be doing weird stuff with keyboards. Okay. Right. It's like complex numbers, isn't it? You know that the people writing the questions have to be careful about complex numbers, so that sort of contains information about the questions, that the questions shouldn't be even like using something that's clearly complex numbers. You know the people writing the questions are doing it so that you can answer with a standard keyboard, so that kind of contains information about the questions. Right, good, okay. We're reversing now. We can make anything. How would I make, so there's a hint here. If I've produced a word, how would you put an A on the front of it? Well, I suppose I would write A on the front, B on the end, and then rule 2 to get rid of the B. And how would I put B on the front? And that's probably some combination of reversing, isn't it? Excuse me. probably some combination, because if I can make this, then I'm done. Refresh and switch. How do I make that though? Ooh, maybe this is hard. Beth, don't encourage them to do ASCII art. I'll get complaints that people are practicing ASCII art instead of doing maths homework. How am I going to make this? I've got lost, chat. How am I going to get B at the front? Oh, you can reverse words now. I've missed this new rule. I lost what I was doing. You can reverse words. Right. So is it something like make AW using the thing above? Make AW using the thing above. Reverse it to get this using rule 3, and then reverse it. Oh no. Reverse it with no swap. So I'm going to use some combination of rule 3 and rule 4. Yeah, some combination of rule 3 and rule 4 is what I want here. Rule 3 reverses, but also does a weird flip, which I kind of don't really want. And rule 4 just reverses it. So I want to do something like I'm doing this for the result of rule 3, which is hard to explain and describe. So I'm just going to put a bar on top of it for like weird. So I want to do something like I can make this. I can make this. I can make this. Using rule 3 and putting the A on the front like I just did, and I know that I can reverse to get, reversing gives me this, reversing this one gives me this because it also flips. Reverse and flip, oh gosh, what am I talking about? Reverse and flip, reverse without flipping, seems bad. Oh no, I need different symbols for reversing and flipping. Oh no. Okay, I should not try to list everything I can make, that's complicated. Okay, so do the flip, put A on the front, flip it again, see what happens. Using 3. Oh, I've got B on the end, that's not what I wanted. So maybe I'll put B, maybe I'll wrap it in rule 4 to get this kind of backwards. So if I'd done that in the first place, if I do that first, if I reverse it first and then do all of this, then I'm good. Okay, so my solution is something like, to get a B on the front, is something like reverse W using rule 4, and then put A on the front. Ooh, and then maybe use rule 3, sorry, I missed a step. Then use rule 3. This is fun, so I'm just sort of messing around with what happens. So just a replacement, if I then use rule 3, I can get something which is like W but with all the A's and B's replaced by each other. If I use rule 3, and then, because my big plan is to put an A on the front using the stuff in part I, previous part, and then flip it using rule 3 to get a replaced kind of W. Oh, and that rule 3 also replaces A's and B's, so just a reverse W followed by B, and then finally use rule 4 to get it back to BW. Good. So that's how you write any letter on the front. Build up a general word like that. Oh, I've gone slightly off the bottom of the page, but talking out loud. Why are there so many hints in this question? There's more than one hint. There's a hint here of how to do this. Is there a previous hint? There's lots of text about what to do. Oh yeah, daft, I can't see another hint in this question. There's a lot of hinting going on, I suppose, in terms of what's already there. Okay, right, I've gone off message, haven't I? Because I've just done a question that I wanted to do, rather than doing all those questions that you wanted to do. which includes such classics as this one. Maybe you saw this a minute ago and thought that calculation sounds like fun. Let's find out. My plan for this one is to draw a better diagram. Oh, great start. A better diagram, and then do a bunch of calculations, adding up some logarithms, because I think I'm going to get lots of rectangles. So we're going from 0 to n, at 0, 2 to the 0, and for a little bit afterwards, 2 to the x will give us something like 1 and a little bit, but won't have made it up to the number 2 yet. So to start off with, we get this kind of thing, until we get to mystery number, where the value of 2 to the x suddenly becomes 2. So when is 2 to the x equal to 2? Oh, silly question, that happens at the number 1. At that point, the 2 to the x is now of size 2, so square brackets around it. The largest integer less than or equal to x is now 2. So before it was 1, now it's 2. These blocks are going to have heights. When does it get to 3? Well, that happens when 2 to the x is equal to 3, which happens when x is log base 2 of 3. And there you go, there's some logarithms. So this is log base 2 of 3 over here. The value jumps up to 3. And I think this happens faster. So we're going to keep going until we get to... Am I right? Or am I being daft? I'm being daft. The bit about a to the I. That's useful notation rather than... It is a hint, I suppose. Sure, because it's part of the solution. Why does it say n up here? I'm not expecting n to be very nice at all, but I suppose, what does that tell me? I should be happy and just keep going. Yeah, so when you get to n, maybe I am being silly. Oh, log base 2 of 4. So there are normal numbers hidden among here. So this next jump happens when x is 2, because 2 squared is 4. So when the power is 2. So there are normal numbers in here, as well as all this weird logarithm stuff. I might choose to write that as log base 2 of 4, which I know is 2, but I might choose to write it in that format. But whole numbers do appear in here, including n. N is the point where you finally, briefly, make it up to the value. So all of these, they keep going up because they're integers, but I'm running out of space. They keep going up until you get to just a kind of value where, just very briefly, pop, gets the next value up. Someone in chat says, "Hi, I'm the maths pizza joke guy." Good to meet you. Right. For a moment, I thought you were saying you were a pizza, which was great. Okay, so there's values here of how tall these rectangles are, and I'm calling them rectangles because we're thinking about integration. Integration gives you the area under a graph, which in this case I'm imagining being built of lots of rectangles. And the question is just going to be, you've got all these rectangles of different widths and different heights. Please add together an expression to get their total area, which we're going to try and do down here. And I'm going to try and do this very carefully. So this one's 1 at the front. Lots of ways to write that, but we're going to go with this. Then the next one's a bit harder. It's log base 2 of 3 minus log base 2 of 2, and I am choosing to write it like that because I think these logarithms are going to collapse down together. That's the width of the rectangle, and the height is 2. And then the next rectangle is log base 2 of 4 minus log base 2 of 3 times 3 for the height. And I'm choosing to write the number 2 like this because I'm hoping that all my logarithms join together. And there's a lot of rectangles. And the last one is log base 2. So the width here, this n I'm going to write as 2 to the n. The previous number was 2 to the n minus 1 underneath chat somewhere. 2 to the n minus 1. And chat's going away for a second, sorry. 2 to the n minus 1. And it had height n minus 1. Because this one, just before we get to the end here, the height is not quite n. These are the things just, x is just less than n, 2 to the x is just less than 2 to the n, so it gets, 2 to the n. It's not n minus 1, it's 2 to the n minus 1. X is just less than 2 to the n, so the height is 2 to the n minus 1. Just less, it gets rounded down to that integer. The good thing about reading it back out loud to chat is that I get to hear it back. Yeah, okay, and there's a simplification for this in chat, where the next thing we need to do is to simplify this until it looks like one of the options in the question. There are some to choose from, you see, and we have to select one of them. Let's tidy this up a bit. Okay. As a request for other resources, running out of Matt papers. As before, anything that you find difficult. I quite like the STEP support program. The foundation modules are on roughly the same material as maths, but there's nothing wrong with the other stuff if you want a challenge, looking at other sorts of maths. Basically, anywhere you can find maths problems that you can't do straight away. So main style. And just to answer a question in chat, everyone's doing the same questions this year. All candidates will do the same questions for MAT. For more information on the MAT format, including which questions to do and how many there are, please see the MAT website, which is in here in chat. There's an information link. Yeah. Oh, does it? No, there's a suggestion, and this is good. I like this a lot. Suggestion in chat: just plug in n equals 1. It's kind of hacking, right? They've got a long, complicated sum to do, and I'm messing up n minus 1s and 2 to the n minus 1s. If you just plug in n equals 1, see what happens. And I guess if you just plug in n equals 1, you're supposed to get 1. So it's cheeky because statements, we're trying to make a statement that's true for all values of n, but if it's true for all values of n, it should probably be true for n equals 1. So if I do that, then I get 1 over here, I get something like 2 take away, I don't know, 2 factorial. Wow, you have to calculate stuff. This is less good. You have to actually think about what these numbers are. I didn't come here to work out 2 factorial, which is, yeah, okay, and then that gives you 1 as well. So, you still have 2 options. Both of these are 1 so far. Maybe then you lose interest in plugging in numbers into this expression. And we should go back and actually simplify this expression. Because I think there's now been long enough that people might have noticed that this reads something like, you have some logs involving 3. We see them again over here with a minus sign and with a slightly larger number. So there's going to be lots of cancellation. You have some logarithms involving 4, and then I suppose in the next term there will be a minus sign, log base 2 of 4, and the number outside the brackets will be slightly larger. So in each case we're going to end up subtracting one of these. This one I'm going to write as log base 2 of 2, so that I can make the point that it appears here, and then it gets subtracted twice. Log 3 here appears times 2, and then gets subtracted 3 times 3. So we're going to end up with almost everything cancels. This pattern stops right at the end, bracket here, sorry. This log base 2 to the n appears lots of times without anything to subtract stuff. So we're going to end up with lots of subtraction. Minus log base 2 of 2 and log base 2 of 3 and 4 and so on, all the way up to, I believe, this one, which has just had this subtraction term on here with a slightly surprising number of minus signs, but then plus at the end here. This one doesn't get to play, it has been included with no corresponding next term to do any subtraction. So now we have quite a lot of subtraction. Yes. I'm aware that I don't quite have any of the expressions up there, but we're working on it. In particular, I'm pretty close to having one of these, aren't I? I'm pretty close to B because I've got some minus signs in front of my logarithms. I don't have a minus log 2 to the n to get this 2 to the n factorial, where I can see 2, 3, 4 up to 2n minus 1. I don't have a log base 2 of 2 to the n, but I suppose I could borrow one of these. Oh, here's one with a minus sign on it, so that I could take out all of these terms, bring all of them together. Log base 2, rules of logarithms, you can bring things together into a common term. If you see things added together, that's a bit like multiplying inside the logarithm. 2 times 3 times ... times 2 to the n, if I borrow that last term over there. So then I still have log base 2 of 2 to the n times 2 to the n. And I got a bit worried looking at the option because I have 2 to the n outside my logarithms. But that's what I want actually, isn't it? I want a 2 to the n here. I'm not assuming that n is a power of 2. I think I got confused a bit switching between n and 2 to the n. So I don't think n is a power of 2. I think that at one point I wrote down n and I should have written down the value of this function for the height of the rectangle, which is something like 2 to the n minus 1 for a rectangle that is not quite as tall as 2 to the power of n. So n doesndoesn't need to be a power of 2. N is the sort of limit of x, and we're feeding x into a 2 to the x function. So we're going to get lots of powers of 2. Okay. So without assumptions about n, I think we're good. I think this thing down here simplifies to n, so I get n 2 to the n minus big factorial kind of shaped logarithm, which starts from b, I think. And I think it all checks out. I don't have a 1 in here, but well, you'll allow me to put in a 1 times, I hope. 1 times doesn't change the thing inside the brackets. Okay, quick breather, because gosh, that calculation's hard. I'm aware I IU question 3 on 2013, and then at least some questions not on 2013 as things to talk about. Cougar in chat has been patiently waiting to go and talk about the last part of 2013, question 3. But it's 6 o'clock, so if you've been looking at a screen for an hour straight, remember to blink, relax your eyes. I'm going to try and drink some water. Give me 2 seconds. Great success. Yeah, okay, symmetries of quadratics. Yeah, that sounds fun. I'll answer that question as well about C and GCSE English. No, we have no minimum GCSE requirements. You might be thinking about English language requirements, and we do have some English language requirements because our course is taught in English. Like, if I can talk. You don't need to meet those before you apply. So if you were previously C grade in English, you could be ready to do a course in English. The rule for English language is that we will ask you for it if we need it as part of an offer. So an anonymous in chat has plugged in n equals 2 as well. I tried to dissuade them. By n equals 2, you've actually had to think about the 3 rectangles that you get in order to get to n equals 2. I think the real trick is to plug in n equals 0. N equals 0, you should get 0 for the integral, which doesn't happen in any of these cases. Ooh. No, it does. It still works in my case, doesn't it? In B, if you plug in n equals 0, 2 to the 0 is 1, 1 factorial is 1, logarithm of 1 is 0, and the other bit, yeah, plug in 0. Good times. I guess C also gives me 0, and so does D. So that's a shame. But I think somebody eliminated those 2 options already. Good. Right. I would like to talk about this idea that Cougar's got for doing the last part of question 3. I know that some people look at the past papers before the live stream, and some people just join in live. So I'm going to quickly review what's going on in question 3 on the 2013 paper, so that we can talk about the last part. Yes, plug in n equals 0 and n equals 1. You heard it here. You do have to think a bit, and it's not obvious that's going to work, because maybe the question setters could choose a function where you have to plug in n equals 2 as well. And then you've wasted loads of time evaluating factorials and stuff rather than actually engaging with the question. Right, anyway, here's question 3. So it's about this area. We've got a cubic, and we know sort of everything about the cubic. It's got roots at 0, k, and 2. I guess we don't know the value of k, so there's one thing we don't know. But given that information, we're talking about this area which comes from integration, and they say in terms of 2 integrals because we're going to be really careful and do things like this where we're integrating up to k, and then this bit of area, well, if you integrate you'll get a negative number and areas are positive, so we should do something like subtract the area of something. So something like that, where you have to fill in to work out what we're integrating. I guess it's just this. Okay, talk about how it's going to be a polynomial of degree 4. I'm going to check it's got a particular symmetry, which comes from kind of strange fact that if you do this operation, or if you just plug everything in, it all works. You can check this algebraically. It's a fact about kind of symmetry of the graph of a cubic. And there's something going on here, but the symmetry is a rotational symmetry, which is not on the MAT syllabus. So I think you can do this by talking about rotational symmetry, but maybe we should just do part 3 algebraically, which means a different value of k, different arguments to plug into the function. So in this case over here, when you see 2 minus k, that means that, slightly confusing, but everywhere you see subscript letter, you write a 2 minus k, and everywhere you see x in the definition up here, this is the definition the first time you meet it, everywhere you see an x, you should write 1 minus t in order to understand what will happen when you plug in 1 minus t. It's a slightly weird notation where there's sort of two things, an argument to the function and a subscript which tells you some particular important number. You've seen that for logarithms, where you have an argument of the function and you have a subscript with an important number. Here, the slightly strange thing is the important number. What if that were 2 minus k? Well, I would look at the place where I write the important number and I would write 2 minus k there in brackets, and I would try not to think too hard about what is k doing? Why is it 2 minus k now? Yeah. Okay, anyway, there's part of the question that I'm trying not to do live on stream because I would do it with a lot of algebra. Okay. Oh, and then they do ask about the transformation. I guess we've now seen that there are these kind of adding ones and doing the minus signs. So you can now build it? Huh, yeah, I suppose you can. Maybe this is consistent with the MAT syllabus then. It's hard, but maybe it's fair because you can see, you've proved this thing algebraically, so now you know that it's true, that there's this combination of whether the minus signs correspond to some sort of reflection. Huh, maybe now you can talk about a pair of reflections happening as a transformation. Okay. So then that's got something to do with how, after you do these transformations, you get a different situation, a of 2 minus k, because after all that effort, you've got to the situation where instead of k, you have 2 minus k. So the area, because you're still looking at a cubic that now goes through 2 minus k instead of k, you now have some areas to contend with. But that's what we were doing in the previous part of the question, just with a different number in here. So if you have a relationship like this, you can write down facts like a of k might be equal to a of 2 minus k. Anyway, last part of the question, which I want to talk to Cougar about, is to explain why, as a result of all that we've done, by working out that this is a polynomial of degree 4, and that it has this fact, using the previous parts of the question, can you work out that a of k must have this format? We know it's a polynomial of degree 4, so there's not very many things that you could write down here. But why has it got this format? Essentially, why isn't there a cube term, and why isn't there a power of 1 linear term in that expression? Which is something that you can think about. Let me know in chat, either if you have an idea about how to do this, or if you're the person who asked me to talk about this question because you've got another idea about how to do this question. This is something for everyone to join in with. We've got, just jumping in at the end here for this question, you've got a fact about A, and you've got a second fact about A up here, and we're being asked to say why it's got this format. What does chat say? What if something goes wrong on test dates? Please get in touch with Oxford. I guess you could get in touch with your test centre as well to let them know that you're not going to make it, but ideally let Oxford know. On the test day is whether that is extenuating circumstances, or I think there's going to be some process to declare any special considerations or things that Oxford should know around your experience of test day. That's for people who've registered but then something's gone wrong. We've had in the past variety of things, from pandemic to typhoon to injury to road closure, that have stopped people from doing a test, and we have guidance for tutors on how they can still shortlist people even if they were unable to make it to the test due to any of those things. Yeah, good. Yeah, so we got this symmetric around. Okay, so ideas are coming into chat, which is nice. Symmetric around x equals 1. I like that a lot. There's kind of the symmetry that we've got going on here, that if you do a translation, maybe that's cheeky, the question's all about transformations, I want to do a transformation. If you do a transformation, it says something like numbers larger than 1 and numbers smaller than 1 behave in the same way. It's not really obvious that 2 minus k does that. Maybe if I define like b of k, something like, yeah, maybe if I write something like a of k is equal to b of, this is just going to make things much worse, isn't it? If I start messing around like this, it's going to make things worse. If I do an extra transformation and bring in another function, but you can do it, if you do the translation, then this is telling you something nice about a function. There's an even function hiding in here somewhere, so it's not surprising we've got even things. Ooh, consider the unit square. What do you want me to do with the unit square? We could just evaluate it. It would be work, and they've already warned us that we don't have to, but you could just evaluate. These things are cubics. You know how to integrate cubics. If you just go and do it, then you'll get a polynomial of degree 4. You're not required, look, twice it says, without evaluating, and then you are not required to calculate. But you can integrate a cubic, so you could just go and work it out. When you go and work it out, you'll get a polynomial in k, and then you'll have to do a little bit of work to recognize that it's in this format. You might have to complete the square, complete the fourth power a little bit to bring the terms together. You'll have particular numbers in here, so it'll be kind of a little bit messy. Okay, Cougar H says, since a of k is a degree 4 polynomial, a of k is, and then they've written down ax to the 4 plus bx squared plus c, which is not what a fourth degree polynomial is, sorry. Because a fourth degree polynomial, just from here, when you see it's a fourth degree polynomial, the thing that you write down is that it might be, I shouldn't use letters like this. What letters am I going to use? Greek letters then, let's go. It could be something like this. With a k cubed term in and a k. So unfortunately, just knowing it's degree 4 isn't enough to get this 4 to power of 0 structure. We need the fact that we need to use this fact in here somewhere. Okay. That's a shame. It is symmetrical, so k equals 1 must be a turning point. Oh wait, hang on, I missed your first chat message. You've got a symmetry argument in there. Only quadratic-like polynomials. Sorry, so sorry, I missed your first message. Only quadratic-like polynomials are symmetric around a turning point. That's quite convincing. You've clearly spotted the correct symmetry. Transforming the points on a unit square will show it retains its shape. What points on a unit square? There isn't a square in the question. Sorry, are we looking at the same question? There is an anonymous person telling me about transforming points on a unit square, but I haven't got any squares in the question. I'm confused. Cool. Oh, maybe they're trying to do that transformation. I could piece it together maybe. Maybe they're trying to do this transformation on... No, I don't know. It can't just be about squares. The question is about this cubic function. You've got to show that the squares move to... Okay, so I would do something like saying I suppose in this factor, let k be 1 plus t. We had all this stuff about 1 plus t, 1 minus t before. So that would show me that a of 1 plus t is equal to, once I plugged in 1 plus t in here, I have 2 minus 1. 2 minus 1 is 1, because 1 plus 1 is 2. Welcome to the Oxford MAT Livestream. So this a of 1 plus t is a of 1 minus t. That's nicer. I considered bringing in a function b, which I shouldn't do. So it's a of 1 plus t is equal to a of 1 minus t, which tells you that this has a symmetry. This has reflectional symmetry. And then there's a question about how much you can then say in the line t equals 1 as a function itself. This one doesn't, because this has got a cubic. This doesn't have reflectional symmetry in the line x equals 1 or anything. But the function a does have a reflectional symmetry. So if you write it as something like, instead of this expression, if you write it out translated in terms of t, maybe, to say, aha, I'm expecting it to be a degree 4 polynomial in t, because after doing the translation, sure, all my alpha beta stuff gets messed up and it becomes a mess, but after translating, I'll still get a degree 4 polynomial. So I'm expecting this to be a degree 4 polynomial in t, degree 4 polynomial in t after doing that transformation here, and then this rule says something like it's an even function, so it can't have a cubic term or a linear term. I think that's probably all we need to say. You could write out an expression with including the missing terms and experimentally plug it in here and here. That would be sort of powers of t. So let's say something like if a of 1 plus t is equal to, I need more letters now, don't I? Let's use random letters from the middle of the alphabet. Mt to the 4 plus nt cubed plus pt squared plus qt. I am really running out of letters, plus r. Then I can say something about a of 1 minus t. And follow that through, I think. It's equal to a of 1. It's supposed to be equal, but also I can plug in 1 minus t into my expression somewhere and show that I get opposite signs on the cube term and the linear term. This is supposed to be true for all t, so you can't have two different expressions for the same thing. Those things have to be 0. That's why they've gone away. Cool, okay. Right, good chat about the last part. Thank you, chat. This question is hard, and it involves transformations that are a bit more advanced than the math syllabus, because it's a multi-part question and it's building up this idea and it gets you to prove this thing. I sort of wonder if this would make more sense if we'd spent time on the stream doing part 3. I slightly regret not doing this bit live, but also it's a ton of algebra and it takes a lot of space, which is not something that I have lots of on the live stream. Good, okay. I know there were requests for questions, including one for something on 2015. I said I would forget, and I have now forgotten. So let's open it up to chat again. We've had a quick look at some long questions there, as well as a couple of short questions on here. We've got about 40 minutes together. What should we do next? Maybe something from 2015. Just to sort of mix up the year. We've got a few past papers available here. What did they say? Let's see if I can find it. If you have interest in doing a particular question, please do let me know. I'm scrolling back through the bit where everyone was telling me about the cancellation. It's good times. Where did we get to? Yeah, can't see it at all. Oh, no, I found it. Maths wanted to do 2015 1D. I did find it. So for 2015 1D, which is one that I picked as well. Good. And there's vote just coming for 2014 1D, which will be over here somewhere, which is about a transformation that is maybe too complicated for the math syllabus. Maybe, I don't know. You can do this in multiple steps, right? But I think this question is, if you know about loss of reflections, then it's easier. Good. Maybe this question is susceptible to an attack like if you put in m equals 1, then it's asking you for the reflection in the line y equals x. So the point should be reflected to over here, 0, 1. So if we put in m equals 1, we should get 0, 1, which this one does. This one does. This one doesn't do. If I put in m equals 1, this one gives me an error message because I'm dividing by m squared minus 1. And this one gives me something fun, which is like 0, 1 just. This one gives me 0, 1, 0, 1. Okay, 3 options to go. But seriously, let's try talking about how we would do this. So I think I would try to find this point. So marking in a right angle. Reflections work using the mirror image, which is on the opposite side to the point on the surface of the mirror. Using mirrors and reflections interchangeably. So I think I would try to find this point P, which is on the line P on the line y equals mx, and P to 1 minus O is at right angles to that line. So the first statement is a fact about a point being on a line, and the second statement is some fact about gradients. I think this line from P to 1, 1, 0, well, I could work out that line as well. So maybe my action plan is something like find line right angles to mx through 0, 1, 1, 0, sorry, through the point that we started with, and then find P where that line intersects y equals mx, and then kind of double up, right? So I've got some vector displacement to get from 1, 0 to P, and then go that far again. So double up. So thinking about it as a vector for the displacement to get from 1, 0 to P. If I know where P is, then I know kind of how far away the mirror is and what direction the mirror is in, or that point of where the reflection appears to be, and then I need to move that far again. And these kind of vectors are equal to move to P and then moving further again. Said differently, right? Similar triangles or something. Similar triangles, here's a similar triangle, here's a similar triangle, just go the same distance again on the other side of the mirror. Reflections. There are some suggestions in chat to try m equals 0 or try -1, which probably kill this, right? So -1, the other options give mad things, but option D gives something sensible, which is to give 0 as the x coordinate again. The others don't do that. And then the correct value for the y coordinate, which is nice. -1's a good pick. 0, is that one fun? It sort of stays still if you put in 0, but the others do that as well. So 0 doesn't help us right now, I think. Actually, do all of them go through? No, not all of them. Okay with 0. This one, there's clearly some design going into the options to check that when you plug in obvious values, you don't immediately eliminate all the options. Good. Designing multiple choice questions is really fun. You never know what people are going to try. Okay. I think this sort of thing, I'm trying to remember if this was in a formula booklet that I saw at some point in A-level, maybe in further maths or something. There's obviously something going on, right? That this has got lots of 1 plus m squareds and 2m's and 1 minus. You know, it feels like Pythagoras. It feels like some sort of square thing going on. That once I've seen this, I feel like I've seen this before somewhere else. Where have I seen this? It is Pythagoras, isn't it? Quick tangent, chat. I know I've already done one, but I want to do another one, which is, I think these might be Pythagorean triples. What am I up to? Let's go. I think there might be some Pythagorean triples hiding in here, which would be cool enough to be worth the excursion. Is this true? is this true? So this would be 1 minus, so this would give me a 1 and an m to the 4, so that would balance. And then the middle term is 2 minus 2m squared. This would add on 4m squared, so then I would get 2m squared over here. So that's true. So there's secretly a Pythagorean triple hiding in there. These are some points where, why has that happened? Oh, because when you do this reflection, you get another point on the unit circle. These have got modulus 1, because the distance from the origin is the same in the mirror. The mirror goes through the origin. The distance is still 1. Right. If you just find the x coordinates, yeah, I've seen similar things in vectors as well. This is the vector 1 minus m squared comma 2m divided by its length, because this thing's got length 1. It started with length 1 and it's been reflected. It's still length 1. So it's a point on the unit circle. If m is rational, then you get a rational point on the unit circle, which is nice. And the rational points on the unit circle are the Pythagorean triples, more or less. So that's why I recognise it. Anyway, good, right. Good tangent. I found some Pythagorean triples, maybe. A squared plus b squared equals c squared with whole numbers. Here they've been divided so that it has modulus 1. But yeah, nice. Unit vectors. Yeah, good trick. Maybe we should have spotted that earlier. Maybe. Modulus. Is it the only one where the modulus works out? Maybe it's the only one where the modulus works out. It's not, it's not always true that when you reflect in a mirror, it's not always true that the reflection will be the same distance from the origin. The mirror has to go through the origin for that to be true in all situations. Right, okay, good. Good question, like the pick. Was that 2014? Yeah, so I've rudely ignored 2015 question 1D, despite it being requested twice in chat by the same person, and it's one of my picks. Here's an integration question from 2015. It asks us to integrate two functions. Part of the trick here is to realise that we can actually do those integrals. They're called functions of x because the integration is actually with respect to t. So when you do the integration with respect to t, you treat x as a constant. So I guess we could bring it out at the front. And then maybe the question is tricky because it's asking us to do something complicated with compositions of functions. G then f. Oh, I pointed at the wrong one, that's confusing. This one is G then f, and the one underneath here is f then G. It's asking us something complicated rather than just saying, hey, please do these integrals, and then think about what you get. We should do the integrals, and then think about what we get. For example, this f of x thing is just this, which is not very mysterious as a thing. It's just this. So add 1 to the power of 3, divide by 3, plug in 1, plug in 0, you're fine, you get a third. Whereas this one is not mysterious. Add 1 to the power, divide by 3. Have I got this? I think I've got this. This would be a bad time to make mistakes. I think it was x cubed over 3. So that's nice. Okay, I think I've got these right. I'm having lots of second thoughts now. Both of them want me to integrate t squared. One of them wants me to plug in x as the limit, and one of them wants me to just multiply by x squared. Yes. Oh, is one of them secretly a scaling? Yeah, no, not quite. Not quite. Not quite. They're not quite scalings of the same integral or something. Anyway, I'm losing interest in understanding what they are because I've now got simple expressions for them, which I think I've got right. I've looked at them twice. We're asked to work out g of f of a, so I'll do that now. G of f of a, that means, well, think about g, you have to cube something and divide it by 3. What do you put inside here? Well, you put in the argument of g, which is f of a. F of a is a squared over 3. Okay, I can probably simplify this. I'll put a note there for it to get back to it. f of g of a says that you have to square something and divide it by 3. What are we squaring? Oh, it's g of a, which is a cubed over 3. Okay, I could probably simplify that one as well. Oops, slightly behind chat. Sorry, chat. So, equal sign, come back to it. A to the 6 over 3 to the 4. Can't be bothered to work out what that is. Whereas this is a to the 6 over 3 cubed. So, I don't think it depends on the value of a. I think that first one's always smaller. So I think the option might be b. But I really feel like I might have made a misstep. So I'm going to quickly check. And you can let me know in chat if you want to get an easy... Yeah, no, it's big because of the thing. I calculated them. I did it. Cool. That felt like weirdly... I thought I'd have to engage with all these inequalities, so I got nervous. I think we're right though. People in chat, let me know. Does this look good? We're right. I'm about to say that 3 to the 4 is bigger than 3 to the 3, so this one's small, this one's large. I'll choose this. Do I have to worry about the sign of A? Nope. I don't know why they've told me that A is positive. Doesn't seem to matter. Yep, can't think of a reason why they would do that. I've got a thumbs up in chat, so I'm going to carry on, I think. There's a good chance that the person who requested this question disagrees with me about the question. I'm giving them a chance to jump in chat and tell me how they were thinking about it differently. It's weird, isn't it? It seems like all of the challenge might be in deciding to integrate these things and then getting them right, fine, but just realizing this is a question where you just calculate f and g, get rid of the integral signs. The question sort of fell apart after that. There's that thing we talked about earlier where you're cautious and you want to engage with the things in the question. I'm very nervous right now. I haven't thought at all about inequalities. The number 1 is mentioned a few times and hasn't turned out to be relevant at all. So you're nervous, you want to engage with the question, make sure you're being very careful, but also you just sort of get on with it and do some integration or whatever. See the things in the question and start thinking, oh, maybe I could calculate those, or just go for it. Good. Balancing act. There were other requests recently. Let me quickly scroll down. They were this. I never did work out where the unit square was. I think it's my turn. Avoiding this. Just as a warning, we've done it before, but just as a warning, some of the past questions have things like the trapezium rule in. The MAT syllabus was updated in 2018 just to remove the trapezium rule, really, and a couple of other changes. I'm avoiding questions on trapezium rule. There's nothing wrong with the trapezium rule. If you know what it is, then hey, there are some challenging questions about the trapezium rule from past MAT questions that you might like to engage with. That's the quote. Good. Okay, so I saw a transformation question and an integration question. I think I'm in an integration sort of mood. What are my other picks? Did I have other picks? Oh yeah, a nice question. What are we at? We've got 25 minutes. It's maybe enough time to do a nice question and then a horrible question. A hard question, I should say. I've got to be careful because otherwise people you can't have favourites, right, when it comes to past questions. They're all past MAT questions and I love them all equally. Even the one about vampires, which there's this question about vampires that, oh dear. Even that one. Right, here's a question about the digit sum. This question is interesting because it doesn't use any of the maths on the syllabus unless you want to. For example, when I say if you want to, when you see 1 plus 2 plus 3, you could think, aha, this is the sum of an arithmetic regression with first term 1 and common difference 1, and I know a formula for these. The formula is, let's see if I can get it right as a joke. Commit to the bit. The formula is n over 2 times the first term plus n minus 1 times the difference, so 2 times the difference, so 4 times 3 over 2 is 12 over 2 is 6. You can choose to use maths from the syllabus, or even more advanced maths if you want to. But sometimes a more straightforward way to do the question. Good, I'm just smiling because I managed to get the formula for arithmetic progression sum correct. You know, the sum of the first 3 terms of an arithmetic progression. Joking aside, let's look at the actual question. How many numbers less than 100 have a digit sum equal to 8? Key observation, those are 2-digit numbers. So we're going to look at 2-digit numbers, which I might write as something like xy for a 2-digit number, or maybe AB. I want the digit sum to be 8, and I have to use actual digits, so there's only a few possibilities. So maybe this is a question about combinations, or choosing things. Like once you've chosen a value for x, there's only so many things you can choose for y if you want the sum to be 8. Good. I like this because the question develops as it goes on. It generalizes, look. So this first part is almost insultingly straightforward. You can just list them, there's not very many. But then it gets harder by asking you to think about slightly harder versions of this question by thinking about what if the sum was n, less than 10, sure, but different value n, so we have a different target to make. And actually this is not very much harder than 8 at all. You haven't really used any properties of the number 8 when you're thinking about the first part. So you can write down the answer happily. And then you get this interesting question with 3-digit numbers and digit sum n. I guess this includes 2-digit numbers as well. Oh, I suppose this includes 1-digit numbers as well, didn't it? 1-digit numbers maybe, fine. Or just 8 would work. Okay, good. And 3-digit numbers. And this is the part where it gets really interesting, because now the answer is quite different, and you've got to think a little bit differently about how, when you're writing down a 3-digit number, if you've got a digit sum in mind, it's not just you write down 1 digit and then you're basically done. You write down 1 digit and then you've got some choices for your second digit, and those choices affect what you've got left over for your third digit. So we might have to think about different cases in order to make that digit sum, or some sort of hidden sum, right? There's a vote in chat for maybe this is a hidden geometric series. I guess I can see a hidden geometric series going on here. 10 or 100,000 forms of geometric series, and it depends what happens when you do the cases. There might be some sort of hidden sum within the sums for you to think about. I'm being vague rather than just doing the question. Thought I'd mix it up rather than just doing questions in front of you. Maybe someone at home is doing this question now, and hopefully they're thinking about cases. What if the first digit is 1 or 2 or 3? What have I got left over? I guess it could be 0, giving you a 2-digit number. What have you got left over with? How many ways you can make n using those remaining digits? Then the question gets a bit specific again and says, restricting your attention to numbers between 500 and 999, not inclusive, with digit sum equal to 8. So then we're going back up again, and this bit behaves a bit more like a kind of, I don't know, newspaper puzzle or something, because you've got the 500 numbers, you've got the 600 numbers, 700 numbers, 800 numbers. I'm losing interest a bit because they've already got digit sum 8, even if I put zeros in. So there's not very many possibilities, right? It's sort of restricted. So then here I could put in, I've only got 1 bit of digit sum left. I've used up 7, so I've got 2 possibilities. And this kind of structure maybe gives you ideas actually how to do the previous part if you haven't already tried it. You sort of get 1 thing here, 2 things here, 3 things here, and 4 things I think here, because you could write 530, 521, 512 or 503, and there's a kind of pattern here and maybe a hidden sum that you could try and do. Okay. Then there's parts here with we're trying to make it more complicated with numbers up to 1,000 digit sum equal to 8 and 1 digit at least 5 We've already found the ones where the first digit is at least 5. What about the other ones? We're mixing this up. So that one of the other digits might be at least 5. Things to think about in there. Good. Okay. So this is an example of a math question where it's not necessarily using any of the maths from the syllabus. It's just getting you to think logically. And it's in the question 5 slot for all applicants. This year, all of the questions are for all applicants. And this is evidence that a question for all applicants might not use maths might not use any particular maths topics you recognise from school. I don't know, unless your school has stuff on digit sum, which I realise now it might have stuff on digit sum. You might be excellent at stuff like this. What's chat up to? Let's have a look at chat. Maths 22222 is talking about stars and bars. And they've got a thumbs up on that, which means someone else is also thinking stars and bars. And I can't see how to use stars and bars for this. And I know that now that I've said stars and bars, I should probably explain what stars and bars is. Stars and bars is a big general technique for splitting up some objects into smaller groups. It's a way to count how many ways there are to do that. The idea is that you have a collection of stars, and separately, to split them up, you have some bars. And as you write things down, you could go star, star, bar, star, star, star. And you see this gives me a way to split 5 things into 2 and 3, using a bar to separate out the objects. The stars and bars observation, the kind of key idea, is that if you have a fixed number of stars and a fixed number of groups that you want to put them into, could be 2 groups like this, or maybe more if you have more bars, all I'm doing when I write down these lines is to permute the symbols star and bar. And any way I can rearrange them might give me an acceptable list of stars and bars. So if the question is, how many ways are there to split up some stars into some subsets, where the order of the subsets matters and where you're allowed to have 0-sized subsets, then the answer is just permutations of stars and bars will give you the right thing. They're thinking about that because they're imagining, I think, the person at the top of chat is imagining that this is like you have 8 stars and you want to put them into 3 digits so that you get a kind of digit sum of 8. Maybe they're thinking about n. So they're thinking you've got 8 stars to use, and the bars are splitting when you stop allocating those to the first digit and move on to the next digit. And if you have a symbol for that, then it stops being. It's a good technique because it stops being the concept of moving on and starts being a symbol for move on to the next digit. Once you have a list of symbols, you can permute them using permutations, combinations, logic to say, well, I'm looking at 6 things. Some of them are stars, some of them are bars. One of them is a bar, so let's move on. Good. You made me explain stars and bars. I hope you're happy. I didn't explain it very well. It's a topic that you could look up if you like. It's useful for Olympiad maths sometimes, I think, if you're interested in that sort of thing. It's not on the math syllabus as a technique that you have to know about, but I can imagine a math question. I'm not sure it's never happened. I think this math question you can slightly choose to use this way of thinking if you like. It's more of a way of thinking than a bit of maths that you learn. That concept switch from the idea of moving on. Like how we had the robot. There was a robot a couple of weeks ago. This won't make sense to people who weren't here a couple of weeks ago, but there was a robot that was moving right and up. And the key thing was to say, aha, we should turn those movements into symbols, and then we're just talking about permutations of symbols. The idea to write down symbols isn't really a maths thing that you learn. It's kind of a parameterization of the problem, which is a separate skill. Good. Let's do it in part 3. Part 3, right, let's go. Part 3. So numbers less than 1000 with digit sum equal to n. There are possibilities for the first digit. N is a number less than 10, so it could be the case that the first digit is just n, and this could be the number n100, n00. But there's obviously more possibilities. We could have n-1 or n-2 or n-3 all the way down to the first number could be 1. And this looks like a long list of things, but actually because n is less than 10, it's quite a short list of what the first digit could be. And then we could ask about the second digit. If the first digit was n, if it's n, then second digit has to be 0. And in fact, the third digit has to be 0 as well. If it's, the notation is going to look weird here, but if it's n-1 something something, then the second digit could be 0 or 1, and then in the next case down, you could be 0 or 1 or 2. So there's more possibilities further down, all the way down to if it was, well, I suppose 0 is here and here as well. Thank you, anonymous person in chat. This list should go 0 at the end because we don't have to have this kind of hundreds digit. I should probably say hundreds digit. First digit depends on how many digits there are. I want to talk about the hundreds digit, which might not be there, which is like having a 0. Okay, if it's 0 hundreds and it's a 2-digit number, then the second digit, that could be anything, right? But it could be anything up to n. It could be 0, which is n+1 possibilities. But then the important thing is that in the third digit is then fixed. You don't get to play any more games. This is crunch time now for the third digit. You now have to make the digit sum be n. So no more playing around games like, oh, maybe it's 1 or 2. Like, no. The digit sum has to be n in total. So the third digit is where we bring it all home, and that's fixed so that the sum works out. We haven't gone past. We've been careful not to have too much so far, but then there's only going to be one possibility to make it actually n at the end. That says then fixed in, I think, my worst ever handwriting. Third digit then fixed. Oof. So all we need to do is count the possibilities here. We've got lots of cases that lead on to these kind of choices, and we want the total number of possibilities, which comes from the total number of cases for the first 2 digits. There's one possibility here. I'm going to count them in pink for the number of possibilities. There's one possibility here. There are 2 possibilities here, then 3, then 4, all the way to n+1 down here. In terms of what we could write for the second digit. So I should add those numbers together, which means beautifully that the thing they showed us at the top about the digit sum of 1, 2, 3, being this 1 + 2 + 3 is 6 thing, that's also a sum that we have to do later on. And we have to do, well, more specifically, we have to do 1 + 2 + 3 + ... plus n+1, which is an arithmetic progression. We're doing the sum of the terms. It's triangle numbers as well, so if you know triangle numbers, this is just n+1 + 2 for 2. Arithmetic progression formula, go for it. Good fun. I suppose that is stars and bars because it's a binomial coefficient. So you're going to tell me something like you have n stars for the digit sum, 2 bars. 2 bars? The bars represent move on to the second digit and move on to the third digit, and you're commuting n stars and 2 bars. Like instructions to the robot. Instead of moving, it's instructions like increment this digit or move on to the next digit. So then you're commuting n+2 things. N of them are the same, and there's 2 that are special. So you're just choosing where to put the 2 bars out of n+2 slots. That's the thing I always forget. Once you put the bars in, you've got a slightly longer sequence of symbols because you have bars in there as well as symbols. Yeah, n+1 choices for the first digit, n for the second digit. Not quite. No, it's not n choices for the second digit because it depends on what the first digit was. If you picked a big number for the first digit, then you don't have very many choices for the second digits. If you picked a small number, you still have loads of freedom. So it's not just a multiplication challenge for choices there. In fact, it's the n+1th triangle number, which is slightly larger. Okay. the last part of the question actually asks you to add them all together, which is just a bit of fun. There's a way to simplify that sum. You'll spot it if you think about adding from 0 to 99 first. In particular, if you write out the digit sums of the numbers between 10 and 20, the digit sums there are just a little bit larger than the digit sums between 0 and 9. And then the digit sums from 20 to 30 are larger again in a predictable way. And oh look, it's yet another arithmetic progression. And we have to add 1 plus 2 plus 3 yet again. Slightly more, up to 9 or something, but you have to do that addition. If you like, that's about choosing all the possibilities and factorising a big sum, but I don't think people really enjoy thinking about that as factorising. Let's do it just in case there's one person at home who wants to think about that digit sum at the end in terms of factorising. This one's for them. What's my zoom level? I want something like that, don't I? Yeah, something like that. So we've got the digit sums of the numbers. I'm writing D for digit sum of numbers from, let's go from 0. Digit sum of 1, digit sum of 2, digit sum of 3, dot dot dot, plus here's digit sum of 10 in case you're interested in that one, digit sum of 100. I haven't left enough space because I need to go all the way to 999, dot dot dot, 999. Okay, so the digit sum, this big digit sum factorizes because in each case we can split this out into the separate digits. So for example, digit sum of 1, 2, 3, which is in here somewhere, is d of 1 plus d of 2 plus d of 3. So there's loads of things added together. Why have I said factorize? What was I thinking? Oh, I always think about multiplying them. Oops. Yeah, don't mind me. This is just easy, isn't it? It's just asking you how many 9s there are, how many 8s there are. Okay, one person at home who was interested in this being a big factorization. Sorry, I think I'm going to let you down. It's just a big addition, isn't it? We're just adding loads of stuff. I thought it would be a big something different. I've seen a related question. Okay. Yes, it's giving Gauss energy, isn't it? Right. Yes, good. There's someone put a sum in chat. I think I missed it, but it was the correct sum, so I should have liked it. Yeah, something like this, isn't it? We're adding them all up. How bad could it be? How many 1s have you got? Oh, so maybe the daft way to do this is to say that there's about, as I write out all of the numbers, I write down about 3,000. I wrote down about 3,000 digits total because that's 1,000 numbers. And if I write the leading zeros, then I write 3 digits for each of them. I'm going to put zeros in, who cares, for the digit sum. So I write down about 3,000 digits. 10% of them are 0, 10% of them are 1, 10% of them are 2. So I think I write each digit 1,000 times. If I write each digit 1,000 times and I'm adding all of this stuff, I should just add the digits from 1 to 9, multiply by 1,000, call it a day. I think it might be 45,000, but I might be wrong. Good. It might be wrong. Good. Let's do a horrible question just to wrap up, or at least a slightly unpleasant question. Where's it gone? I don't know if anyone requested this, but look at this integration question. Isn't this nice? Oh, look at it. It's a fact about a function, and you're asked for an integral of the function. You're not asked to solve for the function. I think you separately can, but it's quite a bit of work. Along the way, while you're solving it, you will either accidentally or on purpose do the question. Yeah. Oh, somebody else got 45,000 as well. That's encouraging. That goes with my, that lines up with my 10%. Ah, I missed a 3. I missed a 3. I no longer fully think it's 45,000. I missed a factor of 3. I maybe mean 135,000. Or 135,000. Sorry. Shouldn't have, I let myself down there with the factors of 10 and 3 in my head. 3,000 digits. I'm writing down 3,000 digits. 10% of them are 1. That's 300 numbers, James. Not 1,000. That's 300 numbers. 300 numbers. 300 of each. I should do 300 times 45, which is 13500. I was so smug. I was so pleased with myself. I know my new guess is 13500. It's a strange way of saying a number. There's a fact about Pascal's triangle in there, which is nice. It's a diagonal number. X is the number of digits. Okay, cool. Pascal's triangle fact. Nice. How long have I got? Ooh, less than 5 minutes. That's not really long enough. Let's give it a go anyway. Idea. This integral is just a number. I know it involves a function, but once you've integrated, you'll just get a number. So we could give it a name. I'm calling it A because I think it's an area up to plus and minus signs and worrying about splitting it up, but whatever, it's just a number. I'm going to call it A. And then my equation contains a copy of that. Because it doesn't matter what I'm integrating, it doesn't matter if I'm integrating f of t with respect to t or f of x with respect to x. That just means something to do with an area on this graph where it's f of t, or the same graph where it's labelled with x and it's f of x, but that's going to be the same integration, right? The same area. Oh, underneath chat. The same integration, the same area. You couldn't see that I drew the same graph perfectly twice. So this thing in the question is the number that I want. I guess I should have seen it was just a number because the options in the question are just numbers. Let's give it a name. So then the equation reads something like this. Or I put the A on the left because that's where I put constants. They belong to the left of the number. It goes over here with the 3. It's playing massive brackets and it's got all these fancy. No, it's just a number. You can go on the left over there with the 3. And then we can start playing games, right? So you've got this thing that's supposed to hold for all x, and that means that I can think about reflecting it or putting in minus x just to see what happens. For every number I could put in negative that number instead. Those are both real numbers. So I've got this like fact, if you like, about what f of 1 is. When I put in 1, but it involves f of minus 1, and f of minus 1 involves f of 1. So there's some kind of simultaneous equation going on here. So this is true for all x. So if you like doing a reflection of the, I don't think I like that, but there's minus x squared is the same thing as x squared. So replacing all the x's with minus x, because it's true for all x, so it's true for negative numbers too. That's a stupid thing to say. So I get this fact. I think we're getting there for f of x maybe being an even function or an odd function or something or other, or something nice happening. I guess I'm getting quite close to solving for f of x, which maybe I don't need to do. Maybe I just need to integrate, right? I have this fact about f, and I want a fact about integrating it. I should just integrate both sides. Also, just integrate. Stop messing around and just integrate the thing. Because then I get a over here from integrating this. I get a over here from integrating it with the values in backwards. Probably. And I get 3a integral of x squared. That over here somewhere I've used the fact that I'm integrating f of x with minus x in, which I think is okay because it's just reflecting it. And the limits minus 1 and 1 are okay, so reflecting it, I'll get the same area underneath the curve after I've done a reflection. Ooh, tricky, but I think this is now an equation where I can integrate everything, and I'll get sometimes with a's in, sometimes without, and then I can just solve for a. I reckon that might be good. But I was enjoying this to sort of solve for f of x. That sounds fun. Anyway, we've hit 7 o'clock, so I think I'm running out of time. Oh, something in x equals 0 would be fun, because it would be the same on both sides. You could get the value when x is 0. It's 6. That's a good fact to know. And then I think if you know a symmetry fact, then you can maybe just guess that it's a quadratic, because look at this x squared over here. If you try a quadratic, that works, and then you can integrate the quadratic if you like. Yeah, these are kind of the same equation. So it's an even function. You should suspect quadratic. Not very many of those. I can't remember what the number turns out to be, so I'm going to take your word for it, which is risky, obviously. 12, 3a, 2a is 12. I don't know. I don't quite know what I get. Factor of 2 over here, 4a. Yeah, it could be. Could be. Right, okay. I think I'm going to wrap up though. Thanks for joining in. I hope you're enjoying working through past paper questions. We're going to be back next week in 166 hours for another episode of the Oxford MAT Livestream, looking at yet more past paper questions. You've seen, if you have tried the papers in advance and you want to talk about particular questions, then that's something that we support a little bit. But also, sometimes I just want to talk about particular questions. We'll see what happens next week. See you around. Have a good evening, and I'll see you in 166 hours. Right, sorry for the abrupt ending, just sort of ran out of time. Right, take care. Yeah, thank you, chat. Bye, Beth. Good job moderating. Beth says good luck. Good job. Right, bye.